In this class we are going to discuss about SR latch. Generally latches are nothing but asynchronous sequential circuits in which they are not having a specific clock pulse. We can say these are unclocked flip flops and these can store 1 bit at a time. So, in a clock pulse it can store 1 bit. We can say these latches or flip flops as 1 bit storage devices, and finally we can say latches are nothing but unclocked flip flops. You can't see clock pulse here. So, see here, this reflects the logic circuit for SR latch by using NOR gates, by using NOR realization. So, I drawn this logic circuit for SR latch. Actually, we can design by using NOR gates or by using NAND gates. So, generally NAND gates are preferred, but in this class we will see one example if we take in NOR gates for designing of SR latch, how it will be. So, we will see in this class. So, now this is the SR latch by using NOR gates. Please keep in mind, when you are taking any latches or flip flops by using NOR gate, definitely you need to consider R first and S next. SR means set and reset. So, you just take reset input in the normal path and set input in complement path. So, this is mandatory identification for designing of latches by using NOR gates. But when you are using NAND gates, you can use S here and R here, set in normal and reset input in complementary tag. But when you are using NOR gates, then you need to give inputs like this only, then only your required functionality will come. The reason is, to get your required functionality, you must give like this. For example, if you given S here and R here, your required functionality is not coming. You can give, but your required functionality is not satisfied means, so that is waste of giving that inputs. That is why when you consider NOR gates, definitely you need to give reset at normal track and set at complementary tag. And here while deriving the functionality of latches or flip flops, definitely, as I told you in the previous classes also, you need to consider your truth table. So, as I told you many times that your truth table must contain your number of inputs and outputs. Here this is a sequential circuit, right. So, for a sequential circuit, what may be the inputs? Generally, for a combinational circuit, we are having some n number of inputs and m number of outputs, but for a sequential circuit, to get the output, it is taking the reference of present inputs and present state also. So, that means, for example, if this is a sequential circuit, the present inputs will be R and S and the present state is Qn. You just forgot about this. This is a complementary track. So, whenever you want to derive Qn, if it is useful, then you are going to this, otherwise do not go for this. So, your aim is to get next state. That means, so here this is present state and you need to get your next state. So, now so this state we are giving as feedback. So, this state means complement of this and this we are giving as feedback. That means, data of present state we are giving as feedback input to that sequential circuit. That means, the inputs are actual present inputs S and R and with this present output Qn. So, these may be the inputs. What may be the output means Qn plus 1 may be the output. So, here we will define the truth table for SR latch. So, truth table. So, when defining, when deriving or when taking the truth table for any circuit, you need to consider your number of inputs. For our circuit, the two inputs S and R and our present state Qn is also taking as feedback input. That is why I am taking like this. So, after processing this Qn to feedback and after giving this inputs, whatever we are getting next, that is called as next state. Whatever we are getting in the same place after processing this Qn, so that is called as Qn plus 1, that is it. So, this Qn plus 1 is nothing but next state. Now, we will see how we are going to take that inputs and all this. So with three inputs, how many combinations will be there means, so we are having, so here 8 combinations we can have with the 3 input variables. So our inputs now here is SR equal to SR and QN. So with this we are having 8 combinations like this, 001, 010, 011 and 100, 101, 110 and 111. These are all 8 combinations with these 3 input variables. Again I am segregating this into 4 parts like this. That means, so here you can observe when SR equal to 0, 0, QN maybe don't care, either 0 or 1. When SR equal to 0, 1, QN may be either 0 or 1. When SR equal to 1, 0, QN may be either 0 or 1. So when SR equal to 1, 1, your QN may be either 0 or 1. So like this I am just segregating. So here first condition I am going to consider, that is S equal to 0, R equal to 0 condition. So this is the first condition I am going to consider here. When S equal to 0, R is equal to 0. What is going to happen? How we are taking Qn plus 1. So here, so that means Qn plus 1, here will be your Qn plus 1 after processing this with this inputs. So your Qn plus 1 is equivalent to, so here you are taking Qn bar. So first you are taking 0, 0, S equal to 0 and R equal to 0. So now I am taking that Qn plus 1 path. To get this Qn plus 1, the 2 inputs are, so it will be like this. So you are having outputs like this. First I am taking this path. So first of all I am taking this path 0 plus Qn, so whole bar. So here you are getting in Qn plus 1 bar place, if this is Qn plus 1, here you are getting Qn plus 1 bar in the next state. So first I am going to consider this path or this path as your wish. So now first of all I am going to consider this path only. For that I am taking 0, that means R plus this feedback 1, that means Qn bar. We don't know Qn bar up to now. So here I am taking Qn bar whole bar. So this is equivalent to you are getting Qn. You are getting Qn. After processing this Qn bar with this 0, you are getting again Qn. That is nothing but Qn plus 1. That means your next state is also equivalent to your present state. Now I am processing that Qn again, means you are getting again Qn bar in this complement part. So okay, this is equivalent to Qn only. So now I am taking here Qn plus 1 is equivalent to Qn in this condition, means, so Qn equal to 0 means you are getting 0, Qn equal to 1 means you are getting 1. In this state of S equal to 0, R equal to 0, you are getting your next state as Qn. That means Qn may be either 0 or 1, whatever Qn value is there, that you are getting as your next state, that is it. So now I am taking my second case. So here I am taking my second case, that is SR equal to 0, 1. So S equal to 0 and R is equivalent to 1. So here in R place I am considering 1. So now I am just going to define what is the next state. So actually present state is Qn. Now with R equal to 1, S equal to 0, what may be the next state? So you need to just process with this one. So I am just taking here, so Qn plus 1 is equivalent to, so R value is 1 plus for this NOR gate another input is Qn bar. So Qn bar whole bar, as that is a NOR gate, you are taking Qn bar whole bar. You know that 1 plus anything is equivalent to 1 and 1 bar is equivalent to 0. So here you will get 1 bar equal to 0. That means, so in case of S equal to 0 and R equal to 1, Qn may be anything, your next state is pulling down to 0. So without having knowledge about Qn, your next state is pulling down to 0. So this is not dependent upon Qn. That means present state, your next state is not dependent upon present state. So that means without having knowledge of this Qn, this is taking as 0 in this condition of S equal to 0, R equal to 1. So our third condition, is equivalent to S equal to 1, R equal to 0. So here you need to consider S equal to 1 and R equivalent to 0. So now in this case I am again considering normal path. So a Qn plus 1, every time you are going to derive your next state with reference of these three inputs, that means present input and present state. So Qn plus 1 in this time is equivalent to 0 plus Qn bar whole bar. So that is equivalent to, so you are getting Qn, but you can observe in complement path. When you observe complement path, that means, so Qn plus 1 bar is equivalent to, so you completed Qn plus 1, that means this output. So I just want to take this output, because by using any one of the input, if you are going to get any value, then you need to try that. So I am just trying here, Qn plus 1 whole bar is equivalent to, so this one, so this gate output is dependent upon S plus, so that Qn, so Qn whole bar is there. So 1 plus anything you know, that is equivalent to 1 and 1 bar equivalent to 0. So here by using this analysis, you can write like this: if Qn plus 1 bar equivalent to 0, obviously Qn plus 1 value here is equivalent to 1. So by using these two, if Qn plus 1 bar equal to 0, definitely your Qn value may be 1. So Qn plus 1 here is equivalent to 1. So that means this is not dependent upon Qn. You are getting value for Qn. In previous case, you are not getting value for Qn. You can observe here. In this case, if you take in complement path also, you are not getting any value. If you are getting value, then you can apply for normal path. If you are not getting value, no need to take complement path. So in this case, and these cases are the example for that. In this case, if you considered when you take in normal path, you got Qn, and once again you are checking the complement path. That means you are getting any value to imply for this, but you can check you are not getting any value there. In complement path also you are getting Qn bar only, you are not getting 0 or 1. But here after getting Qn, we need to check complement path. In complement path you are getting some value for Qn plus 1 whole bar, then it implies Qn plus 1 is the complement of this Qn plus 1 bar. So now we are going for this third case. So in third case, so in 1 0 case you are getting Qn plus 1 is equivalent to 1 without knowing this Qn. So now final case, your final case is equivalent to, so your fourth case is equivalent to S equal to 1 and R equal to 1. So both are equivalent to 1. Both are equivalent to 1 means you can observe, so if both are equivalent to 1, what is Qn plus 1 value? Definitely 1 plus Qn bar whole bar. So this is equivalent to 0. You know that 1 plus anything is equivalent to 1, 1 bar equivalent to 0. So you can go, you just check another path, that means complement path. There also you are getting Qn plus 1 whole bar is equivalent to, so you are getting 1 plus Qn whole bar. So here also you are getting 0. So that means, so here you are getting 0 for both Qn plus 1 and its complement, means it's meaningless. So that's why this state is not possible actually this state is not possible, this is only possible theoretically, but practically it is not possible, and this is called as indeterminate state because the value and its complement is having same value. So, that is not possible. So, that is why we are taking this state as indeterminate state. Now, so I am taking the values. So, here when SR equal to 0, 0, your SR latch is in no change condition. That means the next state is also equivalent to whatever state already in, that state will continue. If we given 0, 0 as input for SR latch, if you given 0, 1 as input for SR latch, it will act as reset. Reset means the value is going to reset, means the value indicated by that latch after giving this inputs is going to 0. That means output of that latch is 0. It is not dependent upon any previous or anything. It is going to reset. For example, in any circuit or LED circuit or there, if you are pressing reset, or for example in your calculator if you press reset, then total value it shows like 0. So, it will act like this. So, this is called as reset state. That means if this latch circuit, if you want to reset, then you need to provide 0, 1 at input, that is it. So, in same way, so if for example if you given 1, 0 as a latch input, so definitely it is going to get set state. 1, 1 means it is going to set. So, otherwise it is going to reset, that means 0, 1. So, 1, 1 of SR latch state is indeterminate state. This state is going to waste in this latch, SR latch. So, in the same way we are going to design SR latch by using NAND gates also. So, you just only have to do one thing, that is every time you need to see for next state. People obviously are going to confuse where means they are thinking this is next state and this is present state. No. So, this is present state and complement of present state. Next state will come here only. After processing these inputs you are getting next state, and obviously this is complement port, you are getting next state complement. So, by using complement or normal track, first aim is to get value, otherwise you are getting Qn or Qn bar in the output. So, you can simplify this truth table like this also. For example, SR, Qn and Qn plus 1, like this is there. So, here in 0, 0 condition I am taking this as don't care. So, Qn plus 1 is equivalent to Qn. Now, in 0, 1 condition Qn is don't care. So, you are taking output as 0, that means reset state. So, in 0, 1 condition of SR latch, so it is going to reset state. Like this they will ask questions. So, in which state SR latch is going to set state, that means 1, 0 condition. So, here you are getting 1. So, in 1, 1 condition without knowing Qn, this will goes to indeterminate state. So, like this way we are going to design latches.